Yes.
Yes, sir.
You
Perfect.
are audible now.
Okay. Okay. Thank you. Thank you very much. Good afternoon to this part of the country world, and also good evening to our extreme eastern friends on the Australia, New Zealand sector. Korea also, it's evening. So we are into the 10th edition of R10Talk. What started as a small baby step in April 2021 has now gained momentum. Today's talk will be on hydrogen as a vital link in energy transition. And today's speaker will be Professor R. Sonde from the Chemical Engineering Department of IIT Delhi. For the formal inauguration and to make the opening remarks, I request Professor B.G. Park, who is the Vice Chair, Membership Activities, to kindly say a few words and formally inaugurate and introduce the speaker too. Thank you, and over to Professor Park. Professor Park, please. You are muted. Professor Park, you are muted.
Good afternoon. Good evening.
Yes, we can hear you. We can hear you. Yes, please.
Welcome to the 10th R10 Talk. R10 Talk is a joint endeavor of IEEE R10 Industry Relations Committee, Professional Activities Committee, Young Professionals Committee, Women in Engineering Committee, Student Activities Committee, focusing on enhancing the awareness of trending topics to the community. I'd like to thank all the committee chairs, especially the Industry Relations Committee Chair, Dr. Sanjay Chaudhary, for preparing this wonderful webinar, and to thank our honorable speaker, Professor Ramakrishna Sonde, for his acceptance to our invitation. Now we are delighted to listen to Professor Sonde's talk, Hydrogen as a Vital Link in Energy Transition, Hybridizing Fossil with Renewable Energy, which is a very timely and invaluable topic to IEEE members. The net zero carbon pathway to solve the imminent climate change issues. Hydrogen is considered as the important element. Hydrogen can come to us with many different colors, such as green, blue, pink, yellow, gray, and so on, depending on its production method. Dr. Sunday will show us how hydrogen can be used as an energy storage material, as well as an energy generator. With the advance of water electrolysis and hydrogen fuel cells, the electricity to hydrogen and hydrogen to electricity conversions can be an important energy transport mechanism. Sure that this webinar will provide a good opportunity for all of us to think about the future of our planet, the prosperity of humanity. Please, Dr. Sunday.
Thank you. Thank you.
Thank you, Professor Park, for making the opening remarks. I would just now request Dr. Sonde to kindly start his session, and over to Professor Sonde.
Thank you very much once again. Warm greetings from my end to all of you in India and abroad who are into this particular conference. Thanks especially to Dr. Sanjay Chaudhary for asking me to kind of talk to this young group. And I'm seeing that there's a kind of a diversity in this particular group, from the students to the professionals, from the industry and academia and all that. So I'm little terrified as to how I should be unfolding the subject to all of you. It's such a kind of a cross section, but with all your permission, let me make an attempt for next 45 to 50 minutes to introduce this concept of hydrogen economy or hydrogen as a transition. Well, just give me a minute to share my presentation, and then I'll begin. Somebody has to tell me whether I am audible and my slides are visible. If you can say that, then I'll begin my presentation.
Yes, it's both, sir. Both. You are audible as well as slides are visible too.
Thank you, sir. Thank you so much. So as I said, I'm really thankful to the organizers for asking me to deliver this talk to such a vibrant community like IEEE. I think IEEE is on the cutting edge on all the requirement of the energy, and you have been looking at it, and it's an honor to be delivering to this kind of an audience. And therefore, when Mr. Sanjay Chaudhary asked me, I thought hydrogen is a very good current topical subject. My focus at this point in time that the entire humanity has to really look at how fast we can actually transition from the current energy systems to the hydrogen-based systems by implementing many pilot demonstration to commercial scale facility, because it's a humongous task to the humanity to abandon the earlier system, because the human nature is not easy to abandon what we feel is something which has been the part of our life for last 3 centuries since the Industrial Revolution. And now to say that, oh, this is not the way of doing the things, you have to do it differently, it becomes an enormous challenge to all the arms of society, including the academia and the policymakers and the politicians and the bureaucrats and the civil societies, and everybody need to be really understanding what is that we are doing. Why hydrogen and why now is a question which will be there uppermost in many of the young professionals who are joining, because many of you may be fully aware why hydrogen and why now. One sentence if I had to say clearly, my dear audience, it is climate change is upon us, and I'm not being dramatic here. Climate change is truly upon us, and this is an existential crisis. I can't describe it anything other than the fact that if we don't address this climate change, we may not see this beautiful we on the Mother Earth will continue, but we as a species, our survival is definitely at stake if you really not address this climate change issue. And therefore, it is now or never situation. So as Professor Parks talked about it, I think that this talk is happening on the eve of COP26 in Glasgow. I don't know whether Dr. Sanjay Chaudhary was planning it exactly to be on the eve of the COP20. All important, because we know what happened in Paris, what happened after that, what happened in Madrid, and now today the entire world's eyes are on this COP26 in Glasgow, and we are waiting with a bated breath how 197 countries of the globe are coming together to actually address this particular challenge. The only way, my dear friends, that globe can address this pathway is on total decarbonization and the pledge for a net zero by 2050. In a country like India, 1.3 billion people, where we are aspiring and we are hungry for more and more and more energy, and that energy has to be made abundant and reliable, and it has to be cheap. And now we are putting a fourth constraint on these 3 terms, that it has to be a green and it has to be a non-carbon energy. You can understand the challenge. A country, a growing country, an aspiring country, a country which is now a 7th largest economy and growing at a double-digit terms, you can understand the pressure on a country like India. And there are many countries on the eastern hemisphere. I don't know to name any one of them, but many of the member states may be participating in this particular webinar. And therefore, now to say that in next 3 decades, exactly in 3 decades, that we need to bring the carbon to zero is going to be very difficult by any stretch of imagination. But do we have an option? I mean, we need to ask that. It may be difficult, it may be challenging. That's what we said when Corona happened. But a global community came together, and in 18 months of time, we could bring it, hopefully keeping the fingers crossed, under control. And this kind of a humongous a human intellect now needs to be collectively deployed to make this happen for sake of future generation. My dear audience, I can't add anything more than the three reasons why hydrogen becomes so very important, because hydrogen economy perfectly fits to address the three issues. It is a decarbonized energy carrier. The beauty of hydrogen is a decarbonized. There is no carbon in hydrogen. It's a decarbonized energy carrier, and the reason that I'm actually saying that hydrogen plays a very critical role, that it also can sponge out CO2 from the air, and best way to build the big technology development that we have to have, which is carbon capture and utilization storage, the almighty CCUS technologies. So if you're talking about CCUS technologies, the only way that you can handle these CCUS technologies is coupling the carbon dioxide with hydrogen. And therefore, there is one on the hydrogen technology, hydrogen systems, which has to now flow into the ecosystem of the nations. And second one is that while doing that hydrogen, it also has to pick up the past burden of all the CO2, which is every year we are now emitting about 39.5 gigatons every year, where the carbon dioxide concentration has gone to 414 ppm, enormously high, 1.5 degrees. We cannot avoid that, and you can see the telltale indicators of the cyclones and forest fires and glaciers melting and what have you. The sea, I mean, every country is facing this imminent climate change disasters waiting to happen, and more happens in the developing nations. And therefore, if you want to say that what is the solution, my dear friends, it is resting in ensuring that every nation adopts this hydrogen as an economy, and that's why the importance. And therefore, when Dr. Sanjay Chaudhary asked me to deliver this talk, I said it's the best way. Many of you may be knowing everything, so pardon me if I'm repeating what is already known to you. But assuming that there are also many young professionals and students and academics who are going to be into this particular webinar, I thought let me make it very simple from the basic, and then I will crescendo into the various aspects of this so-called hydrogen economy. Now, hydrogen linking between renewable and fossil, whether all the future energy, that's the one question, and it's very relevant to this membership of IEEE, where electrical electrons are the fundamental kind of a building blocks of your community. Now I'm saying, hey, look at hydrogen, you have looked at electrons, but now you look at the protons, because the electron and proton coming together is an hydrogen atom, and hydrogen will it now remain as the primary source of energy carrier than electron or electricity, which has been so very, I mean, we have a tremendous amount of the respect for this electricity right from Faraday and Maxwell, when we understood the electromagnetic theory. And therefore, now going away from that, or making this particular thing from electrons to a protons, is what we are talking about, this hydrogen economy. So current status, when you are talking about a large size, I mean, even today in India, you will not believe that though we are building about 80 gigawatts, and there's a huge thrust for a solar renewable power to go up to 450 gigawatts. But when you convert that gigawatt into gigawatt hours and look at the energy consumption, so where you have to discriminate between the installed capacity and the energy requirement, today in India, we are consuming about 9,000 terawatt hours, Indian energy requirement. And in that 9,000 terawatt hours, 6,000 terawatt hours go for the actual energy consumption in the industry. transport sector, residential sector, and commercial sector. These are the four sectors where 6,000 terawatt hours, 9,000 terawatt hours is our total primary energy. 6,000 terawatt hours is our energy which is consumed by the various. I mean, this one. So we have kind of in that 6,000 terawatt hours, only about 1,600 I mean 1,300 terawatt hours is the electricity portion of it, and rest of it is the energy in non-electricity form. So we must understand that when you look at the energy mix at the generation side and at the end use side, electricity forms only about 16% out of that 6,000 terawatt hours. I'm sorry, I'm kind of bombarding you with a lot of numbers, but just to give you an idea that there's a lot of non-electricity demand in the society, in the industry, in the commercial, in the transport sector, where you have energy which is not in the electricity form. So in India, out of 9,000 terawatt hours, 6,000 terawatt hours is the energy consumed, and in that about 1,300 terawatt hours is the electrical energy that goes into this, and rest of the energy is in the different form of that energy. And in that, today what we are saying is that rather than using electricity, everything is now going into electricity, and electricity will in turn convert it into all other forms of energy, whether we have to look at a different way of doing it. And that is when you look at it, rather than this, the current picture, where whether there's a heat network, whether there's an electricity network, everything is in a form where it is all from an inside, outside in kind of a situation. When we talk about hydrogen, what is proposed in a hydrogen economy is that whether it's a renewable energy, whether it is non-renewable energy, whether it's a fossil energy, whether it is a nuclear energy, let us convert everything to hydrogen, and then hydrogen can then meet all the form of requirements, whether it's required for thermal, whether it's required for transport. So you can make hydrogen as a center, and all forms of the energy, whether, as I said, in the four different energy users in the society, you can supply it via hydrogen. The reason is, and I would like to repeat again, that it will ensure that even if that hydrogen comes from a fossil fuel, please note what I'm making a statement. You may find it very controversial statement that I'm making it, but I want to make it to make it very clear that because today again there's a coloration that is started happening. Oh, this hydrogen I don't want. I want this hydrogen, that color hydrogen. I want to make a plea to this particular community that we really don't care, because hydrogen by itself, once you bring this hydrogen, the way hydrogen will manifest itself is always in a highest energy form, which electricity cannot do. Hydrogen can do that, because hydrogen has a potential that it can convert it into the end use, whether it is electricity, whether it's for traction in the transport, or whether it is for the purpose of thermal energy. You will realize that hydrogen can do this conversion at a much higher level. Today, the problem of CO2, my dear friends, is not because of the fossil fuel alone. We are blaming fossil fuel, but the reason for such a humongous problem that has happened for last 200 odd years or 100 years, the exponential rise is because the way humanity has exploited the fossil in the most inefficient pathways. So again, this may not be gelling well with the statement that I'm making, because the two most celebrated inventions, the steam engine cycle, the famous steam engines, or the turbines, and the boiler and turbine, bound by the limitations of the second law of thermodynamics, and the internal combustion engine, again bound by the rules of those Otto cycles and diesel cycle and the Brayton cycles, are the reasons, because of the nature of these thermodynamic cycles, they have got an efficiency of the order of 30%, and the 70% of the energy goes in the form of a CO2. So today, when you are saying that we are a globe, I mean, all of us as a global community are putting about 40 gigatons or 40,000 million tons of carbon dioxide, 50% or 60% of that carbon dioxide is not because of the fossil fuel, but it's because the engine or the pathway that we adopted is actually a cheaper pathway to use that fossil fuel in the form of energy. And those cycles have really brought us to this kind of a serious situation. And I've done an analysis because of the transmission and distribution losses, because of the large refineries, because of all these reasons, the cradle to grave, or what we call well to fuel efficiency, has come down to 12.5%. And that is the reason, my dear friends, you have a problem that is gazing at us, begging for an immediate solution. But when you now change from this status to a hydrogen base, and which is what I'm going to be explaining in my this talk, you will suddenly realize that we are into a very different world, and that is what I'm explaining you. Now, if I show you, this is a little cluttered slide, but if I just show you how hydrogen and electricity as an energy twins will twins transforming as per the demand. If I look at it, that means the globe can now look at two energy carriers. One is the electron or electricity carrier, and one is hydrogen carrier. So look at this complete kind of a very, very symbiotic transfer between electricity and hydrogen. So you can see your electrolysis sitting where you convert power, electricity, the renewable electricity into hydrogen, and that hydrogen is further taken to the gas turbines and generating power. So you have got a cycle here. I mean, I will explain this cycle a little later, but just want to bring it to you. Or you take that particular hydrogen and take your CO2, as I said, it acts as a sponge. The problem of CO2 solving, because there is a legacy CO2 which is present. There is a huge amount of CO2 which will remain till humanity lasts, or till we survive on the this thing. CO2 has got a half-life which is at least about 1,000 to 1,400 years. So it's not going to go away from the atmosphere, which is where the steady increase in the CO2 concentration has gone from 320 ppm, and today it is touching about 418 ppm as per the latest results. And it's a ticking bomb which is waiting to actually explode. And therefore you are looking at this particular, and that hydrogen, which is now completely free of carbon, will be now used in refineries, in the chemical plants, and in the energy sector. So that kind of a conversion, where whether people are using coal into steel plant, people are using the naphtha or a natural gas to many chemical plants, will now replace those raw materials to hydrogen. Okay, so hydrogen will come from both the renewable energy, and later on, as I said here, you will get the hydrogen from also fossil fuel. You take care of the carbon dioxide by coupling carbon dioxide with the hydrogen again. So this is the pathway. My friends, I know there'll be a lot of questions, but I'm just showing this pathway as a part of my journey, how this hydrogen is going to be playing such a key role. And of course, all of you must be knowing, but I still tell you that hydrogen has this beautiful, huge amount of gravimetric energy, because an atom of hydrogen can release about 33.2 kilowatt hours. And you can imagine that 1 liter of gasoline may contain about 6,000 to 7,000. May contain about 6 to 7 kilowatt hours, whereas same hydrogen in 1 kg carries about 33 kilowatt hours. So it has got a very high gravimetric energy content. Only thing is that how to really do is how do you maximize the volumetric, because that hydrogen, how do you really compress it? And therefore, not only hydrogen, how do you convert that hydrogen into a form, whether it could be converted into a metal hydride, or it can be converted into methanol, or can it be converted into ammonia, or the different pathways. I will come to that a little later. But the fact that hydrogen has got energy, and the other important aspect is that fuel cells. So hydrogen, like the electrolyzer, will give hydrogen. Hydrogen will convert it to electricity by a very high efficiency fuel cells, and fuel cell can generate, if you work with a combined heating and power, using the waste heat coming from a fuel cell, you can get an energy efficiency of the order of 75%. There is no device in the world today where at a distributed scale, you can get electricity and the other energy at such a high energy conversion. And therefore, even in the hydrogen, of course, if hydrogen comes from renewable energy, the carbon dioxide is nil. But even if hydrogen comes from the fossil source, if you are able to take care of the CO2, you will realize that that hydrogen will deliver end efficiency at a much higher level of efficiency. And I would never shy away from saying that even whatever form of the hydrogen intrinsically becomes a green energy. Therefore, the four drivers which set for hydrogen is, of course, the cheaper renewable energy. And when the energy is cheaper, you feel that in order to the only problem that needs to be solved is how do you store the energy in large quantities, and hydrogen offers that option of storing the energy into a very large quantities in the form of a grid scale or a captive scale. I'll come to this point a little later. High efficiency cycle based on hydrogen makes hydrogen best option compared to current fossil energy. So I mentioned it, I'm repeating again. Hydrogen, there is no gas turbines, there is no steam cycle, there is no engine which can deliver you an efficiency of 75% in a most flexible manner. And hydrogen, because of this particular capability to work in an electrochemical manner, generates that, and therefore you get a very high efficient cycle. Hydrogen is versatile. It meets all forms. I mean, today it is required for the thermal industry needs. As I said, only 16% is electricity, but there's a huge energy that is required for the industrial application in the form of thermal energy. And today, when you burn coal or you burn biomass or when you burn the other hydrocarbons, you end up in a lot of carbon dioxide and SOxes and NOxes and particulate matter. Whereas hydrogen is such a pure fuel, it does not anyway emit carbon dioxide. It also does not emit any other the local micropollutant, which is creating a huge problem in many of the industrialized nations. And hydrogen therefore gives you a very high efficiency to meet the application for thermal, for electrical, for cooling, for transport, and finally for the cooking application. So it's one of the most versatile decarbonized energy carrier, far superior to the electricity. Carbon capture utilization, I mentioned it again. I'm sorry, I'm just repeating this just to bring you the clarity and importance why hydrogen, because hydrogen can suck carbon dioxide. So if today one way, other than the geological formations or a geological sequestration, which has got a lot of question mark about the safety of that carbon dioxide deep in the earth crust between 10 kilometers, like what has happened in Slipner in the Norway, North Sea, we do not know. Globe may not have so many good reservoirs to park carbon dioxide for the lifetime, thousands of years. So you know that if we're able to convert that into hydrogen, like the way the plants do in an artificial photosynthesis manner. I mean, photosynthesis manner, if you can convert that, there's a good way that you can actually suck all the carbon dioxide. And to do that, hydrogen plays a very important role. So hydrogen has got a dual role to perform as an energy generator as well as absorber of carbon dioxide. This is the kind of a continuous interchange. So wind generator, electrolyzers, hydrogen storage, fuel cells, and fuel cells, as I mentioned, has this beauty of generating electricity at very high efficiency, even at the kilowatt scales, and even at a turn down, any turn down, if there's a 1 megawatt fuel cell at 250 kilowatt, that fuel cell operates at a much higher efficiency. So it has got a very different characteristics, which actually is required. And many times that's what happens. You design it at one point, and when you operate your cycle, whether it's a Rankine cycle or a Brayton cycle, at any point other than the design efficiency, you find the efficiency goes down, and therefore the CO2 emissions go down. Today, there's a problem. When solar energy is high, because we don't have a storage, we back down the coal plants, and the coal plant, which was otherwise generating about 1.2 kgs of CO2, now you'll find it generates more CO2 when it has been asked to operate away from the design point. Whereas fuel cell has the beauty characteristics that at a lower turnout, it gives you a much better efficiency. That's the nature of the Nernst equation. I will explain to it if I have some time about this particular aspect. So hydrogen is the best energy storage when you talk about from a days to weeks to season, and especially rainy season when solar energy is not there. And today you have seen what happens to the coming of the wind and creating a crisis in Europe. You will realize that hydrogen becomes a very, very handy tool operating from a few hours to a daily. You can actually store hydrogen. So compared to pump storage and compared to compressed storage, hydrogen becomes a good energy storage for all the requirement. So just to conclude this part of, there are three sections to my talk. The first section is hydrogen is versatile. Hydrogen is used as a renewable energy storage, and hydrogen is now required in industry, which is otherwise using fossil fuel. You can substitute all the carbonaceous material used in the industry for refinery, steel, chemicals, caustic soda, methanol, with hydrogen. Fertilizers, which is such an important important material, which uses again a fossil-based system like the crude or naphtha or natural gas, can be replaced by hydrogen. There's a gas economy, there's a transportation. All of the transportation can be converted to a hydrogen. And finally, power generation, electricity generation can also be. So hydrogen is a unit that is required. Now, having given you all the basic thing, and I hope at least some of you are converted to the reason that we should go for, globe should go for a hydrogen. There are three, my dear friends, we need to push our accelerator, pedal on the accelerator. Enough of analysis. We should not get paralyzed. We now should get into action mode. This decade, 20 to 30, is the only decade that is available to do whatever is required, because next 2 decades, that is decade between 30 to 40 and 40 to 50, is for completely uprooting the current state and building this new hydrogen economy into the ecosystem of every society. So there are 3 accelerators. One is how do you produce hydrogen, both fossil and renewable. So here I am changing a little bit of a track from a very conventional thinking that all hydrogen should come from only renewable. I'm saying no, not necessary. In many countries where the energy requirements are so high and renewable will not be able to meet that requirement, renewable are infirm. They cannot give you the reliability in the requirement of the power. They will still need fossil, and that may continue for next 3 decades. How do you then hybridize the fossil with renewable and via hydrogen? Okay, so they are not hybridized at the front end, but at the back end you hybridize them by using hydrogen. Second challenge, where we need to understand what the way of storing hydrogen. Do we store hydrogen as virgin hydrogen, liquid hydrogen, gas hydrogen, or convert that into component? And if you ask me, my analysis is that it's best to be converted into some component which may have some small carbon or which may not be having any carbon. And when you convert them, and I'll tell you what we are doing in India on this, there's a huge thrust that's happening by Niti, and I'm a chairman of that particular hydrogen committee to convert that into a form where then it can be transported using the current existing liquid energy transport, which is very important, because in the process of this all transition, it will demand a huge investment. And which pathway puts less pressure on the investment in, because they're all going to be not in billions but in trillions of dollars. Therefore, hydrogen storage and transport becomes important. And then finally, I've said it and I'll say it once again, hydrogen end use is very important. So we need to develop the hydrogen boilers, hydrogen heaters, hydrogen furnaces, hydrogen combustors, hydrogen blast furnaces, hydrogen fuel cells, hydrogen combined heating power stations. So a lot of applications. Going away from the current way the end energy has to be generated. And one caution, my dear friends, many options, and every nation, it may not be one solution fits for all kind of a thing. What happened in case of the internal combustion engine or a steam engine cycle, entire globe adopted to only one way of doing it, because that's what was done in the developed world, and everybody else followed that particular pathway. My submission at this stage, depending upon the geography, depending upon the way that whole energy requirements are there will each nation has to carefully choose, while remaining the hydrogen, the best pathway. We may say methanol. Somebody may say we go for ammonia. Third fellow may say we'll go to a metal hydride. All 3 options will have its own way of doing it. So it's quite a complex task and need engagements at several levels. Now comes let me start about the need of the hour is to build hydrogen infrastructure quickly, and that would include hydrogen from multi sources. So what we are proposing in India is that while we are looking at the renewable energy via electrolysis, that's a given, but we know that today's technology of a proton exchange membrane cell will make this hydrogen will be very expensive. It may be about $4 or $5 a kg of hydrogen, which will not work to give you affordable energy in India, which of course will happen. I mean, we are looking at many other options. We are looking at anion exchange membranes. We are looking at many other ways of a better technology in the water electrolysis, but we are still feeling a biohydrogen, which is available in India in a dispersed manner as a part of our agricultural activity and available as a bio residue or a agro residue, or coming as a residue coming from the municipal solid waste or a refuse derived fuel or a solid derived fuels. We would like to actually propose that green hydrogen can also get generated, because carbon dioxide will be captured in the form of a char and put back as a nutrient back into. It's a very, I would say, a virtuous cycle that we are building of a hydrogen, which will be not generated in the form of a million tons per annum, but it will be generated in 1,000 tons per annum. Like I'm proposing maybe 2 to 5 tons per day of hydrogen, or 1,000 tons per annum of hydrogen built in a distributed manner in a area of about 25 to 50 square kilometers. Dotted of these hydrogen plants can be built across the length and breadth of the country and meet the requirement of a centralized hydrogen coming from a renewable energy and the distributed energy coming from here. So you are having these two. Natural gas is one way of doing it. Of course, the steam methane reformation. There are companies in India which are looking at these steam methane reformation and looking at hydrogen and carbon capture and get a hydrogen. We are working in, again, as I said, Honorable Prime Minister of India has declared coal gasification as a main way, 100 million tons of the coal gasification as a clean coal pathway. We are not going to abandon coal because that's a natural resource. India is seeking for a climate change in the presence of India's energy independence, and therefore coal becomes a very important thing. But the way how do you reinvent coal itself in a clean manner so that you get the energy, you get hydrogen, you can get other things, and you capture the carbon dioxide, convert that carbon dioxide into a useful product, again using a hydrogen, is the pathway I'll explain to you a little later, and then of course other forms. So I feel that green hydrogen coming from bio waste or a municipal solid waste, which is kind of solving two problems at one time, because otherwise we burn all this agro residue or landfill all the solid waste and creating a huge amount of environmental problem. Whereas if we are able to extract that and not simply convert and burn it in the form of a electrical energy in a conventional steam Rankine cycle, if I'm able to convert that into hydrogen, probably that's the best way you can valorize and create a very healthy way of generating hydrogen of a highest value. And this, when we do the analysis, you will see later that it can meet the requirement of less than $1 a kg. So even a gray hydrogen or a brown hydrogen is green, because as I said, the pathway for hydrogen is much higher when you go through a gasification route. So as I explained to you, India is looking at, because we don't have natural gas, so we can't afford to use hydrogen from the natural gas with the capture or something, and therefore we are looking at a bio waste or a agro residue to convert that into hydrogen. I will not go to this flow sheet because I think I've got another about 10 minutes to kind of come to I leave it to the organizers, because if I have to finish by 10 minutes, so I will not get into the details of this particular flow sheet. But what I'm saying is that as the production side of hydrogen is concerned, what we are feeling that be ideal is that we will have a renewable energy which are in the big solar parks, and there whatever goes into the grid will go, but whatever is the excess renewable energy, we would like to convert them through a water electrolysis into hydrogen. That could be in terms of the several thousand tons of hydrogen, because India has got a plenty rich solar energy which is available, wind energy available, and the grid will not be able to absorb that energy. There's a huge amount of analysis and modeling. Monte Carlo methods are used as to how this grid will behave and what kind of a excess energy need to be done as a storage on a hourly and a weekly and a seasonal wise. There's a enormous work is happening in IIT Delhi with many of the industry partners to work on this. This is a favorite topic of IEEE community. I know that very well, and many of your community scientists are working with us in terms of understanding how do we really ensure what is the best way to design an electrolysis. But we are also proposing in that particular pathway a pathway of putting coal, and after capturing, we get that hydrogen and work that hydrogen and get that hydrogen as a additional hydrogen from the renewable energy. Initially, for next decade or so, more of hydrogen will come from here because this is going to be the cheapest hydrogen, which will give you a higher efficiency. So I'm not taking carbon completely out of the equation right now. I'm still having carbon into the equation, but that carbon is not delivering more end energy, and therefore the CO2 emissions will definitely come down for a given energy consumption. I hope you understand what I'm saying here. When it's renewable power, of course, there's a carbon part into the renewable energy, because whether the water electricity or renewable energy, the making of this electrolyzers or panels still are consuming some coal energy or a carbon and a fossil energy, and therefore there is a energy carbon penalty here. There's a carbon penalty here, and there's a biomass which you thought that on the top there will be large plants, and at the bottom there are smaller size plants which will be done, and that hydrogen is what we are planning for the country. The thrust that we have put for this development, which is what I'm submitting to the government and various industry partners are working, the technology what we are developing should be robust, reliable, designed in a phase, because hydrogen, the inflammable nature of hydrogen has to be understood. I know it can be managed. Electricity was also talked about as one of the hazardous things, but the global community has now adopted to electricity as though it is kind of your friend. And similarly, how to make hydrogen a friend so that there are all the aspects of the safety and the leakages and its implications are very well taken care. There's a deep science. Whether it's the sensors, whether it is putting the various systems and putting those hydrogen quenching requirement, and there are number of new things which are available today to make your system very, very robust, because it's very important that we understand the nature of hydrogen when it is stored at a high pressure, and therefore I'm proposing non-high pressure storage, but that's something which are there. The technology should not have any control elements, because if you start talking about using the batteries which uses lithium and cobalt and various materials which may not be available, rare earths, then there's a problem, and therefore we should develop a technology which we are developing, and of course the cost should be under $1. And that is the way that we are planning a demonstration plant near my institute. IIT Delhi has got an extended campus in Sonipat. We are trying to build a demonstration of a technology. Again, my dear friends, you must pardon me to rush through this particular thing at this stage, because I've got how many minutes now? Another 10 minutes I got. I'll try to kind of finish most of this, but this is the distributed energy plant, so that this hydrogen plants at a distributed scale, which will deliver it at less than $1 or $2 per kg of hydrogen, can be worked as a cooperative movement. Like you must be knowing that India has one of the global leading nation for a dairy. How we started as a milk deficit to now a leading milk producer in the world. We are the number 2 largest milk producer. Similarly, it was done through a cooperative movement. It's a very exciting story. I'm not going to share that story because we completed 75 years of our milk revolution, white revolution, what we call. And similarly, hydrogen can happen when all these farmers who have got about 7 acres or 10 acres or of the land, or about 5 hectares, if you are comfortable with the hectares as a measurement of the land, you can see that you can develop a hydrogen-based energy plant which will add to their additional point. Now, there are many, I'm not getting it, as I said, there's a one technology development that we are doing where a biomass or a RDF is a municipal solid waste converted into refuse-derived fuel, and that is converted into hydrogen. I will, pardon me, and I'm sharing this presentation later on, so I will not go into the details. And this is the technology development that we are doing it. As I said, while we are developing this, if India has to look at, and I'm sure there will be many countries who are in the same position as my country is, we will need more and more hydrogen, because people should get used, because people ask, if I generate hydrogen, who is going to use it? You can't put it as a side fuel along with natural gas as a hethane or a hydrogen methane into a internal combustion engine. So you need to develop a lot of hydrogen use, hydrogen transport, hydrogen handling, safety, regulation. And how do you really scale up this hydrogen? One is biomass and one is from a fossil fuel. So we are developing along with IIT Delhi, we have got a big group, and it's about a $7 million funding from the government of India, where we are developing coal to hydrogen. Right now we are going from a coal to methanol as a kind of a way to convert hydrogen, because essentially you get coal to hydrogen, and subsequently, because you don't want to use hydrogen in its virgin form, we couple it with a very low carbon intensity and get methanol. And that is the plant I showed it to you, which we are building at a sufficiently high scale. And we have been asked now to scale it up to a much higher level. Again, I'm not getting details. Hydrogen from water electrolysis. So these three pathways: one is a biomass pathway, one is a fossil pathway, and one is a water electrolysis. And water electrolysis, my dear friends, is another rich area of research and innovations. Huge amount of innovations are happening here, and that would require itself one full course lecture on what are the alkaline fuel cells, what are the proton exchange membrane cells, what is solid oxide electrolyzers, and what is anion exchange membrane cells. So again, I can get into the details of the fundamentals of technology, where we are developing right now, where most of the technologies are in the PEM cell, and that will cost you with a very high energy consumption of 4.5 kilowatt hour, will cost you about $6 a kg of hydrogen. And therefore, so these are the four different electrolysis processes that are now available for getting hydrogen from water electrolysis. Need of the hour, as I said, as much as you have to put hydrogen from the biomass, you have to put hydrogen from the renewable energy, there is also need to actually scale up this hydrogen from the water electrolysis. So there is a plan that European Union is looking at a 40 gigawatt about 200,000 kgs of hydrogen. There's a relationship based on, as I showed in the previous chart, the energy consumption and the hydrogen that is generated in the system. So as far as the generation is concerned, I'm saying there are three pathways a country like India has to follow, because you need to implement hydrogen and its utilization sooner, and that particular thing demands that we actually build up the hydrogen infrastructure. Maybe 30 years from now, it could be only the renewable energies which will generate hydrogen. But currently, for the next 2 or 3 decades, we would need hydrogen to come from all the sources, because coming from biomass, coming from agro residue, coming from coal, coming from natural gas will actually build the scale to the hydrogen generation at a reasonable cost, so that you will be able to actually build an economy around hydrogen. Second portion, my dear friends, is how do you store hydrogen? Now that's a $1 million question. Do we store? Because as I said, it has got a highest gravimetric energy, but it does not have enough volumetric storage, and therefore people have been looking at, can we convert it into a different product? I have done my analysis whether hydrogen should be carried at a 600 bar pressure, so that you have the target of at least about 1,800 kilowatt hours per liter of hydrogen, which you compare it with a battery, it will be about 6 or 7 times the energy storage compared to a lithium-ion batteries. It is very high, but it's still much lower than what currently gasoline or the other crude oil is carried. But that's the best way of fixing hydrogen, because you carry a high intensity and then you can use the existing liquid fuel transport network, which is already available as a part of your distribution of hydrogen. So there are many work. I mean, again, as I said, this gives you what is the kind of a kilograms rupees per kg of hydrogen. These are all calculations which you have developed, but let me not bother with too much of a details analysis of the costing of what is the best way, whether we should carry as a pure hydrogen or whether we should carry it as a liquid hydrogen with a small amount of carbon or with no carbon. So end up this one is we need to do a techno-economic safety analysis on the mode of hydrogen storage and its distribution. So it is extremely important that how do you really handle hydrogen and how to dispense hydrogen is the second important aspect that that we as technocrats need to discuss for coming to a consensus what is the best for every country. So it cannot be, again, as I said, a universal solution. What is good for India may not be good for Germany. So Germany is going for ammonia, but we are proposing that maybe methanol may be the best way to go for it. The debate is not kind of concluded what is the best way that you need to transport hydrogen from the storage point to the end use point. But we have done some analysis that if you are developing a distributed hydrogen plant, which is, let's say, about 2 tons per day, which can meet the energy requirements of, let's say, 25 square kilometers, maybe even hydrogen by itself storing at about 200 to 250 bar, which is not a 600 bar, which is the ultimate thing where about 6% of the gravimetric energy density is carried per kg of the energy carrier, which is what the global target that is set. But at about 200 to 250 bar pressure, the target may be less, but since it is not a large requirement, the transport is not too much. The optimization is showing that you don't have to go to such a high pressure. So that's the other way of doing it. So plants are distributed. Hydrogen can be stored into 200 to 300 bar. No new infrastructure is required. For large-scale hydrogen based on coal or renewable energy, we may have to explore whether 700 bar hydrogen storage is better or it has to be converted into methanol or ammonia. I've done my analysis, but I'm not presenting that analysis, but just take it from me that this is something which works well. Of course, there are a huge amount of research which is going on in every institute which is having an international standing, whether it's going to be liquid hydrocarbon carriers or a metal organic frameworks, which are away from the commercial deployment, but a lot of work is happening on that area. Hydrogen to carbon dioxide, as I said, one is hydrogen generation, hydrogen conversion for end use, but hydrogen to CO2 is another important aspect where hydrogen plays a major role of absorbing carbon dioxide from the atmosphere or absorbing carbon dioxide from the steel plant, because the current assets cannot be abandoned and they may not be easy to transport or convert that into removing their current fuel into hydrogen. They may still emit CO2, and can we convert that, capture that CO2? So there are 3 pathways that we are looking at it. One is carbon dioxide to methane, carbon dioxide to methanol, and carbon dioxide to ethanol. I mean, there are a huge amount of, there are many research institutions in India, including my own institute, which is working on this development. So this is a little busy slide. End of the day, what you are doing is that there's a carbon coming from a point source, coming from power plants, steel plants, and you have got a water coming from whatever as a hydrogen source, and then you use your renewable energy or a nuclear energy, and this energy converts this directly into methanol. So you don't really get hydrogen here. You get hydrogen as its methanol as a carrier, because methanol is about 72% energy is coming from hydrogen in methanol, and that's a highly hydrogen. And that methanol can be either used as a chemical, because large number of chemical is a precursor to make so many chemicals. So carbon dioxide can be permanently sequestered, whether it's in the form of a polycarbonate, or whether it's in the form of a lubricant, or whether it's in the form of a solvents, or whether it's in the form of a F&B industries. So that carbon can be used there, and rest of the carbon can go for your energy generation, both for the stationary as well as for the mobility applications. So today, fuel cells sitting in the car can give you a lot of way to get to a much better zero carbon emission vehicles, and that CO2 is emitted here at the end, and that can go back here. So that's the way ultimately in 3 years time, when you say net zero CO2, right now some CO2 is coming from outside, and this CO2 is getting circulated, and you will get a beautiful virtuous cycle where CO2 acts as a carrier. It does not get itself into the atmosphere. But I'm just leaving this slide because I might not be having a time to actually discuss this. So I think I'm coming to the last portion of my talk, which is end applications. Okay, I've talked about the production, I've talked about the distribution, and I have to talk about now the end applications. So there are three developments: hydrogen as a thermal energy, hydrogen as a distributed energy, and hydrogen for a mobility energy. So these are the three energy needs. And I would like to ask the organizers how much time I have got, sir, and then accordingly I will conclude my speech. Do I have 5 minutes?
5 minutes, sir. 5 minutes, okay.
Thank you, sir. So I will complete in next 5 minutes and then go for the Q&A. So essentially, this is another big topic of how do you really develop. So there's a huge amount of work which is happening on hydrogen as a boilers. I was earlier at CTO and member of the board of executive council in Thermax, and we were looking at whether it's going to be electricity boiler or a hydrogen boiler. So we clearly understood that a hydrogen boiler is far more effective boiler than going for a solar PV based boilers if you want to abandon all the coal and natural gas or a fuel oil, furnace oil, diesel oil based boilers. So this is the way that a boiler way that is done, where you can use this energy, convert that into hydrogen. Hydrogen is carried into this, and you've got all the developments of the boiler. So this is fairly simple, but hydrogen as a fuel cell becomes the main backbone of hydrogen economy. So as I said earlier, hydrogen from the biomass and the water electrolyzer, at the end use, it is fuel cell all the way. And a fuel cell operating with at a certain temperature, and I'll come to that certain temperature, and a rejected heat, converting that into HVAC requirement. Today in India, about 36% of our energy requirement is to meet the heating and cooling requirement of what we call HVAC. A tropical country like ours, cooling requirement is major. Even in the so-called winter months, 50% of the country still runs on the air conditioners, and therefore you can convert them. The total energy conversion is of the order of 75%. I will not get into the details, but I can tell you that you are now abandoning what is dearly called as a second law of thermodynamics or a Carnot efficiency, and you are now getting electricity using this equation of the Gibbs-free energy. And I'm not getting the fundamentals. There's a different course I conduct on masterclass on fuel cells, but just want to tell you that you can get an efficiency of 94%. So compared to a Carnot efficiency, you get a much higher efficiency, and we have developed the fuel cells which are dedicated to the nation, and this is something which we did it for India's strategic forces, and now we are building what we call it the high temperature proton exchange membrane cells for the stationary applications. This particular fuel cell uses methanol as a fuel. It generates hydrogen on an onboard reformer. This is the reformer configuration, and that reformer generates hydrogen, which goes into this particular fuel cell. And that fuel cell is actually not a conventional, what we call the low temperature proton exchange Nafion, where Nafion is imported, where here every component is indigenously built. The Atmanirbhar India is available, and here the energy that is available can be converted to meet the requirements of the cooling and heating. Cooling during the summer and heating during the winter is a global product, and that can really give you a very high efficiency. And I feel that when you compare to a battery vehicles, fuel cell vehicle, I mean, that's one is the stationary application. Fuel cell vehicles is one of the very, very important development because of the high energy efficiency. Hydrogen infrastructure is got a better energy density, long distance driving range. So today you don't have that anxiety about what is the nature of the batteries, how much charging that you have to do, how do you swap the batteries, the safety of the batteries because there's a liquid electrolyte, what happens in case of a high temperature, because people are all designed for a cold climate, but in India conditions of 70 degrees, 60 to 70 degrees, which can happen in a closed portion. There are many uncertainty of this thing, where fuel cell driven systems becomes a very important development, and a lot of work is happening for maybe it's for a city battery is the good thing. For urban transport, battery is good, but for a long distance, for a commercial vehicles, for the trucks and buses and all that, we have done our analysis. We feel that fuel cell acts as a better one. And when you see the development that have happened in the fuel cell, like the way it is happening in the case of batteries, both are competing. These are all the cutting edge technology development that is happening, and these are all methanol based fuel cell are something which are doing it. So coming to an end, yes, now to look at hydrogen, as I said, that because of the problem of the climate change, we need an alternate decarbonized energy carrier. But in the next 3 decades, that decarbonized energy carrier will still come from partly from the fossil and partly from renewable, and both of them will generate hydrogen. That hydrogen will go into various energy usages, as I mentioned. It will also go to capture carbon dioxide, which can again generate some fuel, or it can be used as a permanent residence for carbon dioxide in the form of polymers or polycarbonates, or it can be converted into urea or whatever that is required. So there's a partial kind of a sequestration, terrestrial sequestration, and partial it can be used as a fuel where the carbon dioxide can be recaptured at the end. So this is a complex network that we need to build. And that's where there are many pathways and many demonstration of technologies are required. Hydrogen and fuel cells become an important part. Safety and regulatory framework is very important, and manufacturing sector, I think, has to play a major role in this particular infrastructure. So way forward is the challenge globally is how to replace the current energy systems. It's not that easy because so much we are used to the current easy convenience of a current system to replace with a hydrogen. But there are a lot of there's a body of work which is happening in industries, in research institutions, in academic level, at all the TRL levels from 1 to 10. My submission to all of you is that there are a lot of known systems available at TRL 7. How fast we can push them from 7 to 9 to 10 is very important, where the policymaker, the funding agency, the regulatory people, the academicians, the industry should come together and develop the standards and regulatory framework to take care of the safety. Promote R&D. There's a huge amount of exciting R&D work which is happening. As I said, artificial photosynthesis to get your hydrogen, metal organic frameworks to use hydrogen as a sponge. I mean, look at the beauty of this MOFs, and there's a huge amount of thrust for using MOF as a wonderful medium to store hydrogen. I'm not getting into what is MOF, what are the synthesis, what are the work, and when will it happen, this one. And of course, CO2 water conversion, as I said, that if there's an engine which can take this CO2 from the air and use water and convert that into a thing, and there are, I mean, I can tell you, I would like to assure you that there's they agog with this kind of work which is happening. But the only delivery of this high-end work, and we can reach the net zero, is brace networking at many levels, which will enable us to come up with the groundbreaking new technologies, making hydrogen a dream in next 3 decades. So my only wish and prayer in this happy season leading from our Festival of Lights to the Christmas is let us collaborate. We must learn to happily progress together or miserably perish. Man can live individually but can survive only, says our one of the important Atharva Vedas. With this, sorry for this little running over time, though I was at a breakneck speed, but I wanted to communicate everything. I close my talk. Thank you very much.
Thank you, sir. Thank you, Professor Sonde. Can we have some few questions from the participants, please? Sir, I
Sure.
can see one question that has been posed. How is hydrogen used to suck out carbon dioxide, and what is the process?
Yeah. So essentially what you do is that there are 2 ways. One is the electrochemical way, which is known as solid oxide electrolyzer, where you use carbon dioxide and water. You don't use hydrogen. Hydrogen is happening within that engine, where you convert that CO2 into CO and water into hydrogen. What is known as the outcome of that is not hydrogen, but what we call synthesis gas. And that synthesis gas, there's a proportion of hydrogen, 2 moles of hydrogen or 3 moles of hydrogen, 2 mole of a CO2, and then you send it to some process, I mean, which is known as the gaseous fermentation process. There are 2 pathways again there, a gaseous fermentation, or you can send it to a transition metal catalytic process. Copper zinc is what is conventionally used at about 60 bar pressure, and you can convert that into methanol or ethanol or into any kind of a product. So that is the way that you convert carbon dioxide and hydrogen, and that's the way that actually you absorb carbon dioxide from the stack or from the emitting point and convert that into methanol. So there's one way. The second way is, of course, I mean, you don't have to go to this electrolyzers where you use the renewable energy. There is the other way, which is known as, it is still in the researching stage, where you actually use a metal organic framework and then put your catalytic process. And there are magnesium pathways, there are calcium pathways, there are 3 or 4 pathways where you can convert this particular carbon dioxide using hydrogen and getting that into your whatever products that you want to go for. You can get polycarbonates, you can get lubricants, you can get fuels, or you can get a precursor to many chemicals. So these are the 2 clear pathways where you can sponge out carbon dioxide using hydrogen, because the affinity between carbon dioxide and CO2 can be enhanced by using this catalytic process.
Okay. Any next question, please? You can put it in the chat box. Questions from the participants, please.
Yeah. No, I don't think there's any other question, Dr. Sanjay Chaudhary.
Yes, I also think so, that there are no such questions, so that we can move on to the next step. That is, I would request Rajendra Asthana ji to kindly make the closing remarks and propose the vote of thanks. Please.
Hello,
Rajendra ji.
am I audible?
Yes, yes, you are audible, sir.
Thanks a lot, Professor Sonde, for your very informative and absorbing talk. As you said, it's a necessity of today to keep pace with development, including climate changes. Hydrogen has the highest carbon-free energy, and hydrogen is available in plenty, but not in elemental form, and need to be extracted from water or hydrocarbons. Being cheaper renewable energy, it's a potential source for energy. Besides electrolysis, hydrogen is produced from the fossil sources like coal, crude oil, biomasses. Besides being efficient, cost is also low. Hydrogen is being used in renewable power. Also, new uses of other types of hydrogen, that is blue, green, gray, brown, etc. The hydrogen and fuel cells are being developed for industry, transport, and other energy applications. Some of the main drivers for utilizing hydrogen could be cheaper renewable energy. Hydrogen energy storage is better than batteries. Hydrogen has a better cycle efficiency. It has no emissions. Hydrogen is a versatile fuel for all sorts of energy uses like thermal power or traction. Gives higher efficiency for larger power plants compared to coal-fired power plants. It's also useful for long distance transmission because the transmission losses are less. It's useful for solar battery systems. It's used for water electrolysis, hydrogen fuel cells, and other energy devices. But there are some precautions and safety required. That is, hydrogen is very inflammable and explosive. But it is taken care by designing and engineering of hydrogen compatible materials that makes the hydrogen safer than handling of fuels like diesel, petrol, and natural gases. Besides that, other main roles of hydrogen are, these are energy generators, and it also absorbs carbon dioxide. And some of the main accelerators for use of hydrogen are hydrogen production for both fossil and renewable energy, hydrogen storage and transportation, pure hydrogen and its carriers, hydrogen end uses, both stationary and mobility applications. Techno-economical safety analysis for hydrogen storage and distribution. I think this, considering all these factors, the use of hydrogen is getting more and more in industry and power generation. Thank you. I also propose a vote of thanks at the outset. I profusely thank Professor Ramakrishna Sonde for delivering us the talk, and also our other IEEE dignitaries from Region 10 who have joined this talk. Professor B.G. Park, then Savitya, Sanjay, Jia, and Lance Fung, who have been part of this. And I also thank all the organizers who has helped in organizing this talk. Thank you all. Over to you, Sanjay.
Thank you, sir. Thank you. Thank you, Professor Sonde. Please accept our small memento that we have offered you on behalf of Region 10, because this is a time of pandemic and we could not meet physically, but given the earliest opportunity, we shall do so.
Thank you very much for giving me this.
So it's a memento that we will be sending to you. Thank you very much.
Thank you, sir. Thank you very much. Wish you all a very happy festival season.
Our next episode of Region 10 Talk is on next Saturday. That will be delivered by Dr. Jing and MD. By profession, she is a medical practitioner, but she is pursuing her electrical engineering with MIT. So we will have a chance to know how electrical engineering has penetrated deep into the medical sciences. Thank you very much. Thank you very much. And we come to the end. So please do connect with us over LinkedIn, Facebook, and YouTube. And please do send us your feedback regarding the quality of the webinar and also your choices for the next webinar topics. Thank you very much.